In the previous presentation, we discussed about the Ohm's law, and in this presentation, we will be talking about the electric power. So basically, what is electric power? So we define the electric power is the rate of doing work is known as basically the power. So this rate of doing work is basically the transfer of energy. The transfer of energy from one form to another form. And in case of electrical power, if this energy is converted from some other form, to electrical energy in a device, so such kind of components is known as basically the sources, which provides the power to the circuit. And in other form, we means that from mechanical to electrical or from chemical to electrical, then such sort of components are used as sources which can provide a power, which can deliver a power. And if the electrical energy is converted to some other form like thermal energy or mechanical energy and some other form, then such kind of components are used as a load or a sink. And such kind of components are used to absorb the power. And we will be discussing soon that which kind of components are used as a sources and which sort of components are used as a load or a sink. So from this general definition, we can write down the equation of power is equals to the rate of doing work, and this work done is basically the transfer of energy, which we represent by del U, in this case by T. The transfer of energy per unit time is called power. To understand the electrical power in a more brief way, let's consider a simple circuit in which we have a resistor which is connected across the terminals of the battery, and the conventional current is flowing from the positive terminal of the battery towards the negative terminal of the battery and passes through this resistor. So as a result of this current, there must be voltage drop across this resistor. So as a result of this voltage drop, there must be a potential difference across this resistor, and let's say we have a potential at this point is V1 and potential at this point is V2, and conventionally we know that we consider this positive sign at its high potential. So in this case, electric potential at V1 is greater than the electric potential at V2. So as we discussed in the video of electrical potential difference, that if there is a potential difference across the terminals of a resistor or any other component, there must be a drop in electrical potential energy. And in this case, we represent at point 1, let's say the energy is U1. And at point 2, the electrical potential energy is U2. And we know that the electrical potential energy is equals to the charges which passes through this resistor multiplies the electrical potential difference at that point, and in this case Q dot V2, the same charge is at this point multiplies by the electrical potential at this point. So the electrical potential at this point V1 is greater than the electrical potential at this point V2. So from this relation, we can easily say that the electrical potential energy at U1 will also be greater than the electrical potential energy at U2. And this drop in electrical potential energy occurs because when this current positive charge passes through this resistor, and we know that the property of resistor states that it provides a position to the flow of current. So as this current passes through this resistor, so it converts its electrical potential energy into heat or thermal energy, due to which it causes the difference in electrical potential energies. So from these two relations, we can easily state that the potential difference V is equals to V1 minus V2. the electrical potential at V1 minus the electrical potential at V2, and the difference between the electrical potential energies is equals to U1, the energy at point 1, minus the electrical potential energy at point 2. So by putting these two equations here in this equation, we get del U is equals to Q into V1 minus, instead of V2 we can write Q into V2. So here we have Q common in this case, so let's take Q common. We get V1 minus V2, and we know that V1 minus V2 is equals to del V, which in this case is V. The potential difference between these 2 points is V. So we can write down del U is equals to QV. So by putting this equation here in this equation, so we get the power equals to, instead of del U we write QV divided by T, and we know that the rate of flow of charges is equals to current. The rate of flow of charges is equals to current. So instead of this we can write down the current. So power is equals to IV. So this is the main equation, or the basic equation of electrical power, and its units is volt ampere, or simply watt, after a James Watt. So by using Ohm's law we can write down this equation in two other ways, in which the first one is P is equals to I. So using this equation here, V is equals to IR. So putting IR instead of V here, we get IR. So the power equation become I square R. This is another form of electrical power. So by using this relation of Ohm's law, I is equal to V divided by R, we get P equals to, putting this here in this equation, instead of I we can write V divided by R into V. So we get P equals to V square divided by R. This is another form of electrical power. So we can use these three relations to find out the electrical power. So there are two important points about electrical power which you need to be remembered to avoid any confusion, in which the first one is, if you have a component and you don't know the what the component is, and the current is entering at the positive terminal of the this component, and let's say V is the voltage across this component, then the power of such kind of component is positive, and we can say that this component is absorbing the power. And the second point states that if we have a component and we don't know what the component is, and the current is entering at the negative side of the component and leaving the positive side of the component, and here we have a voltage V across this component, so the power in this case would be negative, and we can say that this component is delivering the power, delivering the power. So these 2 points are very important about the electric power. So if the power is positive, then the component used is absorbing the power, and this component is called as a load or a sink component, a sink. And if the power of the component is negative, then it means that it is delivering the power, and this component is acting as a source. To understand these two components, let's consider this example. In this example, we have a resistor and a voltage source. This voltage source providing the power to this sink or this load. So in this case, this voltage source delivering the power, and the resistor is consuming or absorbing the power. So you can see that the current is entering at the positive terminal and leaving the negative terminal. So the power in this case is positive. So we can say that the resistive component always absorbing the power, and here in this battery case, the current is entering at the negative terminal and leaving the positive terminal. So in this case, the battery is delivering the power. To understand these 2 points in a more brief way, let's consider the example in which we have a current which is entering at the negative terminal, which is 6 ampere, and leaving the positive terminal. And we have a voltage across this component which is 10 volt. So the power in this case is negative because the current is entering at the negative terminal of this component. So the current here is 6 ampere and the voltage is 10. So the power of this component is minus 60 watt. And we can easily say that this component is delivering the power because the power of this component is negative. So it's all for today's presentation, and in the upcoming presentation we will be discussing some more example about the electric power. So if you have any doubts, ask in the comment section. See you in the next one.